Let's start the new article, use of phasor method in an AC circuit. So why it is necessary to study the use of phasor method in AC circuit? Because this method can be easily used to find out the phase relation between voltage V and current I. So actually in this particular article we will find out the phase difference between voltage V and current I. So as we have studied the different case, for each case the value of this phase relation will be different. So I am starting my analysis with taking the first case of AC circuit containing only resistance. And such kind of circuits we have observed, and in that we have also obtained the value of current and the value of impedance. But in this case, for circuit containing only resistance, the phase difference between voltage V and current I is 0, and hence the phasor for voltage, that means the rotating vector, I have given you three names for a particular vector which is rotating. So first was rotating vector, another one is phasor, and the third was a rotor. So any one word I can use. So here the phasor for voltage and current will be in the same direction. And such kind of characteristic we can see from the graph. So here there is a characteristic is shown in which the phasor of voltage and current are in the same direction, means on time axis or whatever the quantity you have taken in this direction. The phasor of voltage V can be drawn by knowing the phase difference between V and I. So the notation or the representation of phasor for voltage V depends upon the phase difference between voltage V and current I. Now we will study the different case in which the circuit is containing only inductor. So in this case, what we have studied in the current and impedance obtaining theory. So by use of this inductor, the current I lags behind the voltage in terms of phase by the angle pi by 2. Or the same statement you can write in this way: the voltage V leads the current I in terms of phase by angle pi by 2. But here the rotation is taking place, so you have to consider pi by 2 radian. And if the current I is represented in the x-axis, then voltage V will be along the positive y-axis. And this can be shown from this characteristic graph. So as you can see from the figure, the current is in the x-axis. So the voltage will be always in the positive y-axis. This is the positive y and here is the negative y. And the phase difference is pi by 2 radian. Now let's move on to the third case. AC circuit containing only capacitor So as we have studied in the previous case, the current I leads the voltage by phase of pi by 2, or in the other words, you can say that voltage V lags behind the current by phase of pi by 2. And in this case also, if you consider the current I should be represented in x-axis, then voltage V shall be represented in negative y-axis. So this is just the opposite case of that in inductor. So here the characteristic is shown in which current is represented in positive x-axis or any kind of x-axis, but the voltage V is lying in the negative y-axis by the angle difference or by the phase difference, particularly of pi by 2. Now we will study LCR series AC circuit and also derive one phase relation for that. So LCR series AC circuit. But before we start to analyze this kind of circuit, just recall the characteristics of voltage and current in the above discussed case. So first of all, I am consider the direction of current, and here the voltage in the AC circuit containing only resistance. Then comes the AC circuit containing only inductor. So here is the voltage of inductor, and opposite to that, here not L, it is the direction of current. So this is the case of AC circuit with capacitor only. Now I am giving you a arrangement of LCR series AC circuit. So this is the LCR series AC circuit, but in this you cannot directly judge the actual direction of or actual phase difference between voltage and current. So we have to make some characteristics for voltage and current by means of phasor method. Here the applied voltage is V, that is distributed in inductor, in capacitor as well as in the resistance. So this is my first equation for the applied voltage. Now suppose the phasor of current I is represented in the x direction. Then the phase diagrams for each component can be given by the following figure. So here you can see the direction of voltage which containing only the potential difference between the resistance, and here the voltage consisting of VL minus VC. So I have directly taken the potential difference between the ends of inductor as well as the potential difference between the ends of capacitor. So it is obvious that from this figure also the direction of voltage is also the combination of VL plus VC plus VR. And now if you want to find out the value of V square, then you can write the equation directly in this form, because now inductor and capacitor are shown in the single direction. This actual V, from the figure I am writing this arrangement according to the Pythagoras law. This V square is equal to VL plus VC whole square, or here particularly minus sign will come because it is the potential difference, and the negative VC is added to the voltage of inductor, and so according to the Pythagoras theorem this equation comes. Now if I am supposing that the maximum value of current is Im, and the voltage across the resistance now I can write down as Im into R. Similarly, the voltage across inductor is written in terms of Im into XL, because it is the magnitude of reactance, and similarly the value of VC I can write down as Im into XC. Now substitute all this value in equation number 2, we will get, therefore V square is equal to Im square XL square minus Im square XC square plus the value of VR square, that is Im square into R square. Now I am taking Im square common from both the terms. So inside the bracket XL square minus XC square plus R square. And so the applied voltage is given by applying the square root on above equation. So it is under root Im into XL square minus XC square plus R square. Now here the value which you have done here as directly XL square, actually it is not XL square, but outside the bracket there is a square, so you have to correct it. So XL minus XC whole square, here also XL minus XC whole square. And so this is the equation of applied voltage, and here under root Im square is coming. When it comes outside of the square root, it will become Im under root of xl minus xc whole square plus r square. So this is the third equation for applied voltage. If we take V is equal to Vm, then the maximum current Im is equal to V over, or sorry, here Vm over under root of xl minus xc whole square plus r square, that is equal to Vm over, this is the magnitude of impedance Z, and hence the value of maximum current has been founded. Now, if you see the figure of the characteristic, then the voltage difference between the phasors of, or the phase difference between voltage V and current I is given by delta, and therefore if VL is less than VC, then the current lags behind, sorry, it is leading now because the VL is less than VC. So what happens if VL is less than VC means the value of current will be higher because the denominator is getting smaller. So current leads voltage by phase delta, and the opposite case to this, when VL is greater than VC, so current will lag behind the voltage by the phase difference delta. But what is this phase difference? How to find out the value of this phase difference? So we have the value of slope formula, that means tan delta vertical arm upon the horizontal arm. The vertical arm is VL minus VC and the horizontal arm is VR, if you recall the graph of characteristic. Now the value of VL is IMXL minus the value of VC is IMXC divided by the value of VR is IMR. From numerator and denominator, IM will be cancelled out. So it is XL minus XC over R. And now I can find out the actual phase difference. Delta is equal to tan inverse XL minus XC over R. This is the phase difference of voltage and current, from which you can generate the characteristic. And now we will solve some illustration related to this topic.